You're welcome. All right. So now the topic before us is magnetism and magnetic field. All right. So before we actually discuss magnetism and magnetic field, first, what is a magnet? Okay. How do we define a magnet? Now, a magnet is simply a substance, okay, or a material that has the ability to attract or repel another magnetic material. Okay. So it simply means that anytime you bring a magnet close to another magnetic material, a force will be experienced. And that force will be that of repulsion or even attraction. All right. So magnetism is that force of attraction or repulsion that is being exerted, okay, whenever a magnet is being close. It's actually brought close to another magnetic material. Okay, so now fundamentally, the same way we have the fundamental law, okay, of electrostatic, we also have the fundamental law of magnetism. All right. Okay. Basically, I would say that that is actually a characteristics of magnetism, very major characteristics of magnetism. Now, as you notice that a magnet, okay, will always have two poles. All right, the north pole and the south pole. So a magnet does not exist as a single pole. There's always two poles, and of course, the pole of a magnet is that area or the region of a magnet where the magnetic force, okay, is concentrated. All right. So where the magnetic force tends to be stronger is actually concentrated. So the fundamental of magnetism is that actually said that like poles, when you bring like poles together, okay, then you are gonna experience a force of repulsion. Okay, so like pole repels or repel. So as you can see here, bringing north pole close to a north pole in this diagram, all right, you will discover that there's a force of repulsion. All right, then okay, while unlike poles, unlike pole, unlike pole actually does what? Attract. All right, so please take note of that. Okay, so that is the basic law, okay, or the characteristics. And that characteristics of a magnet, okay, apart from when you bring that magnet when you bring the pole of that magnet to a like pole, there will be going to be a repulsion, right? You discover that whenever a magnet is actually suspended, okay, we always want to point in the parallel, it will align itself parallel to uh, in the axis align, okay, at an axis of north south, north south direction, in the axis of north south direction, okay, which of course is actually parallel to the same direction of earth north south. Of course, you know that we have what is called the cardinal point, right? Where you, for the earth, we have this as a cardinal point. So the earth is actually divided into this geographic cardinal point that is north south. Okay, of course, here we have the east, we have the west. So if you actually suspend the magnet, all right, it will tend to east axis, okay, north south axis tend to be parallel to this earth axis, but in opposite direction. So that means if I suspend the bar magnet, all right, the bar magnet will actually align itself in this direction, having the south to be in this region and the north being at this other region. Okay, so which actually explains the fact that the earth is actually is made up of actually a big magnet. All right, so that means every bar magnet on earth is being influenced by the earth magnetic field. All right, that's just simply by the way. Let's actually now discuss magnetic field. All right. So what is a magnetic field? Excuse me. Okay, so now, of course, a magnetic field actually describes that region in the space where magnetic force is being experienced. Region in the space, okay, where magnetic force is experienced. All right, so the region in the space where magnetic force is being experienced. Okay, now such magnetic force, okay, is being experienced due to the presence of a pole, right? A magnetic pole. So now, since we cannot actually isolate a pole always, a magnet always exists as two pole. That's why it's called dipole, the north and south pole. All right. So now, but in our study, we'll always consider each of these pole individually. Okay. So and our reference pole is always the north pole. So now, invariably, now if I'm actually describing magnetic field around the region, I'm describing the force experience around that region, a region, okay, where force is experienced due to the presence of a magnetic north pole. So in the case of study, okay, for my analysis to actually be simplified, I'm just going to be looking at, okay, I'm gonna isolate the magnet to just a pole, right? The same way we can isolate a charge to have just a single charge. So if I have this magnet, let's say just a north pole are placed around a region, okay, around this region, this north pole is going to actually create magnetic field around this region, okay? So it will create a magnetic field around this region. So that is why this magnetic field that this north pole is create around this region, if I should bring another pole, be it the same, uh, like be it a like pole or even an unlike pole, this pole is going to experience a force, okay, around this region. Why? Because, excuse me, this is a region of magnetic field. Okay, all right. So now, we cannot actually see magnetic field. You can't see it whenever you bring two magnets together, okay, you will discover that there's going to be a force of attraction or repulsion. You don't really see that force because it's not a contact force. You don't see what is actually causing that force, but you discover that there's going to be an attraction or repulsion. So then, how do we actually represent that force? All right. So for us to actually represent the force or represent the field, a magnetic field, we use a line, an imaginary line, known as magnetic field line. Okay. So we actually apply what is called magnetic field lines, or you call it magnetic line of force, magnetic field lines. All right. So magnetic field line is simply that imaginary line we can actually draw in a magnetic field. All right. That indicates the direction of the magnetic field, because a magnetic field is a vector quantity. Okay. So for us to represent the direction of that or the force, the direction of the force that is acted, that is being exerted in the magnetic field, all right, since we can't see it, we can actually use an imaginary line. Okay, it is easy for you to draw that imaginary line. Just take, for example, you just have a bar magnet, all right, excuse me, please pardon me, we got a bar magnet. This bar magnet, okay, of north south actually creates a magnetic field around it, but we can't say it. But if we should bring an ion filing around this region, you discover that ion filing will actually, okay, we align in a particular direction that will make us to draw an imaginary line, okay, which indicates that yes, of course, there is a field created around this region. The ion filing now gives us the direction of the field. The way the ion filing just tiny grounded pieces of iron. Okay, so the way the ion filing will actually align themselves around this particular region of this magnet will actually shows us how to tell us how to draw the magnetic field line. All right. Okay. So now let me draw the magnetic field line of a bar magnet. All right. So if I should draw a magnetic field line of a bar magnet, this is exactly how we actually do that. Now, the characteristic of a field line is that a field line will always emanate from the north pole, then of course terminate at the south pole. So that means the force is always from the north pole, then of course towards it will not terminate at the south pole. So just in case you're being asked to draw such in exams, okay? So the arrow will always draw the arrow at the center, and of course the arrow should be pointing towards away from the north towards the south. Okay, so now with what we have here now, we can simply say that the direction of the magnetic force is just the same direction, okay, of the arrow. All right, so from the north to south. Now, apart from drawing this line that start from the north to the south, okay, um, we can also draw another line. And that line, okay, didn't actually reach the north. It actually, okay, it didn't reach the south. It emanated from the south, okay, then it moves away. The same happens here. This moves away. I have this. So they actually moves away from each other so that at the center now you have what is known as the neutral point. Okay, so neutral point in a magnetic field. All right, excuse me. The neutral point in the magnetic field is actually the point um where two opposite two opposite line of force, are you okay, actually cancel out. Why? Because they actually move, why the magnetic field, okay, is equal to zero. Please let me put that again. A neutral point is a point in the magnetic field, okay, where the magnetic force is actually equal to zero. Why? Because the line of forces, okay, opposite line of forces move in opposite direction. That way, actually canceling out to create a neutral point at that particular region. So this is a neutral point and this is a neutral point. Are you okay? So because this is north pole actually trying to get to the south pole, but it moves in the opposite direction, and this arrow, okay, is this arrow comes is end, right? So now in between becomes the neutral point. All right, so please take note of that. So this is the magnetic line of force of magnetic field line for a bar magnet. Okay, this is a bar magnet or a dipole. But what if I have two isolated magnetic pole, not, and of course, let's say two like poles, not come together. Of course, you know what will happen. There's gonna be a force of repulsion. So the line will move away from each other. Okay? There's going to be a force of repulsion. So which now creates us, because of this now, you discover that if you are being asked to indicate the neutral point, so this point now becomes the neutral point. Okay? Neutral point. All right. So if it is, of course, if it is for south pole, okay, south, the same thing happens. Okay, now the only difference between this north is the fact that when you are drawing it, you have to indicate the arrow. The arrow of the north is always outward. Okay, the arrow of the north is always outward. but that of the south will move inward. But at the end of the day, what you still gonna experience, okay, what you still experience here is gonna be that of repulsion, but arrow is pointing inward. All right. Okay. All right. So that's basically magnetic line of force. Now let's actually proceed. Okay. So the next subtopic we are going to be looking at, we could look at magnetic flux. Magnetic flux. Okay. Now you discover that for a particular bar magnet, okay, the strength of this magnet, okay, is actually dependent on the number of line of force. So the more the number of line of force, the more strength that this you will get out of this magnet, the more strength of the magnetic pole. So magnetic flux is actually the number of lines, total number of lines, total number of line, number of line of force. Okay, that is actually measured around, okay, the area of a magnet. So if I should count the number of line of force around the area of a magnet, that will give me the magnetic flux. And the symbol for magnetic flux is actually, we use this symbol phi, okay, and the SI unit is actually Weber. The SI unit of magnetic flux is Weber. Okay, so please take note of that. All right. So which simply means that the number of line I'm gonna count around a magnet, all right, will tell me the magnetic flux of that particular magnet. So okay. So now we can also define another parameter known as magnetic magnetic flux density. Magnetic flux density. All right. Now this time around, the symbol of this one, the symbol of magnetic flux density is B. Okay. Now, magnetic flux density, the density of magnetic flux is actually given as the magnetic flux, okay, divided by the area, perpendicular area, magnetic flux all over perpendicular area. Okay. So now, if I have the total number of field lines, which of course is the magnetic flux, passing a particular perpendicular area. Okay, let me use this as a passing this perpendicular area, right? So if I'm being asked to evaluate the flux density, all I just need to do is to divide the flux, okay, the magnetic flux, and the area through which the magnetic flux is actually passing. All right. So magnetic field density is given as magnetic flux. All right. Then divided by the area. Okay. So now the SI unit of magnetic flux density is actually is measured in Tesla. All right. That is by abbreviation T. I hope that is well understood. So please take note of this because we are going to be using it. Okay. Now, before we now look at let's look at magnetic field strength. All right. Now, before we actually discuss magnetic field strength, okay, okay, let's just discuss magnetic field strength. All right, so now the symbol for magnetic field strength is H. All right, so now what's magnetic field strength? Now, magnetic field strength is always given as is equal to magnetic force. Magnetic force experienced by a unit pole. Magnetic force experienced by a unit pole. So I use M to represent a unit pole. Okay. Now I don't want to actually dive deep into this magnetic field strength. All right. So invariably now, if I want to write the SI unit of a magnetic field strength, it is actually simple gonna be Newton because magnetic force is measured in Newton and a pole, okay, a unit pole will actually produce 1 Weber, right? So the unit pole produces 1 Weber. So the pole magnetic field strength the is given as Newton per Weber, Newton per Weber, okay, because magnetic pole actually produces flux. We measure the magnetic pole by the number of flux it actually produces. As already you know that. Okay, the strength of a magnetic pole depends on the number of flux. So if I'm looking at the magnetic field strength, which of course is the force exerted divided by magnetic pole, and that's going to be going to be measured in Newton per Weber. All right, so just write down the formula. We are going to be using this formula later on in the tutorial. We just need to get the important parameters. Okay, so now here I'm going to be actually be stating the relationship between relationship okay, now between these two parameters, and that is we are looking at the relationship between the H magnetic flux uh, magnetic field density, magnetic field strength, please pardon me, okay, and of course the magnetic flux density, okay. Now, this particular relationship will tell you that these two parameters, magnetic field strength and magnetic flux density, they are related. Okay. In fact, if you want to measure how powerful a magnet is, it is going to be based on these two parameters, magnetic flux density and the magnetic field strength. Okay. So the relationship is this. I don't want to prove any formula. Okay. Too much formula here. All right. So the magnetic field of any magnet is actually given as permeability, okay, of the medium, then multiply by the magnetic field strength. By the time you multiply the permeability of a medium multiplied by the magnetic field strength, you have converted it to a magnetic flux density. Now, of course, let me write down. Already you know what the B represent, okay? The B represent magnetic flux density. Magnetic flux density. Okay, this symbol that looks like you, okay, is a symbol that's called the permeability of the medium. The same way we have permittivity for uh, electrostatics or static electricity. In magnetism, okay, we have permittivity in electric field. Okay, in magnetic field, what we have is permeability. So permeability of the medium around that magnetic field. All right, depend on the medium. Okay, for air, if we are looking at air, if the medium is just simply air or vacuum, right, then that medium, the permeability of the medium is what is known as absolute permeability. Okay, we use U0 to represent that. We call that absolute because it's called absolute. Why? Because the medium does not have any significant material, okay, that can actually influence the magnetic field around that region. All right. So air or a free space does not have any obstruction or any influence on the much influence. Just put it this way: air or even a free space have the lowest influence of magnetic field, and that is what we call any region, okay, that is just made up of air or a free space, we use absolute permeability to represent that, okay. And an absolute permeability is actually a constant, all right. It's a constant, which of course, I'm going to give you the value of the constant. Okay, so is the constant for absolute permeability is equal to 4 pi times 10 raised to power minus 7. Okay, let's leave the SI for now, but let me just write the constant down. Okay, so 4 pi times 10 raised to power minus 7, which simply means that if what we are dealing is just a free space, that's invariably the permeability we are discussing, we are going to be looking at, okay, is just simply going to be the absolute permeability, all right. But if we are not looking at free space, we are looking at another space. Let's say the space around that region probably is actually of let's say oil or any other material, okay, any other material medium that is neither air or even a free space. Then at that point, the permeability is actually given as is going to be a factor, all right? It's going to increase. Okay, so anytime you have a medium that is other than air or free space, permeability of that medium will increase by a factor known as relative permeability. So in that case, now I have to multiply the absolute permeability of free space by a particular factor, okay, depending on the material that is used in that medium. So this particular factor UR, okay, for convenience, let me call it U, but this symbol is not really U, okay, we call this symbol mu, but for convenience, okay, for simplicity, I will just give it a name. All right, the important thing is for you to know what that symbol represents. Okay, so the symbol UR is what we know as relative permeability. Relative permeability. Okay, is the relative permeability. So which simply means that in as much as we are dealing with different material medium, okay, other than air and or free space, we have to multiply by a particular constant known as relative permeability. For example, if you are dealing with paper, all right, paper has its own relative permeability. If it is oil that is in that medium, it has its own relative permeability. If it is water that we are actually discussing in that medium, it has its own relative permeability. Okay, so please take note of that. Okay, but if we are dealing with free space, no other medium, then what the permeability simply at that point is just going to be the absolute permeability. I hope that is well understood. Okay, basically, for now, I think I need you to actually take down, okay, go through this video again, understand these basic uh, parameters, okay, and of course the definition. Then we are going to continue in the next video. Okay, so see you in the next video. Thank you very much.